All right, we are in 4.7. We are continuing our study of functions. What we're talking about today is rates of changes. So the start thinking part says, here are some recorded temperatures at 3 different times on a winter evening. So it's recorded at 4 p.m., 6 p.m., and 10 p.m., and it has the different temperatures there. It says Tyler says the temperature dropped faster between 4 and 6, and Maya says it dropped faster between 6 and 10. And you are supposed to figure out who you agree with and explain your reasoning. So at first, when the students looked at this, they looked at the overall temperature change. So between 4 and 6, there was a change of only 8 degrees, and between 6 and 10, there was a change of 9 degrees. So a few of the students just flat out said, it must be between 6 and 10. I agree with my. But what they weren't thinking about was the fact that we're looking at rates of change. Even though it is more, 9 degrees is more than 8 degrees, the 8 degrees happened only after or over 2 hours, whereas the 9 degrees happened over a period of 4 hours. So when you actually account for that, it's going to change things. We then talked about the key idea. You can see the key idea there is talking about rate of change can be thought of as slope. And slope could be thought of as rise over run, change of y over change of x, so y2 minus y1 over x2 minus x1, or change of dependent over change of independent. When we're looking at this and we're talking about the temperature and the time is going to be independent and temperature is going to be dependent. The temperature is going to change depending on what time that is in the day. So when we actually found out what the rate of change was here, we found out that between 6 and 10, it was only down by 2.25 degrees per hour, versus between 4 and 6, it was down by 4 degrees per hour. It's super important to make sure that you have your units here so we can figure out what the rate of change is actually talking about. Then we moved on to this part right here. This is saying that we have a graph, and the graph is giving more data points during that exact day. So you can see sometimes the temperature is going up, sometimes it's staying the same, and so on. We were supposed to be finding the average rate of change between noon and 1. So if you take those 2 points on the graph, you could just figure out what the rise and run is. And if you find that out, it is a rise of 1 degree and a run of 1 hour. So it's 1 degree per hour. You could also look at the table on the side, and you could see that the temperature change was 1 degree going from 18 to 19, going up, and then it was 1 hour was going by. So it's still 1 degree per hour. When you're looking between noon and 4 p.m., you can ignore the points in between. If you actually calculated all of those different slopes and figured out what part of time they were actually going to be at those slopes or those rates of changes, and you averaged them all together, you would get the average as if you just went over and picked the point at noon and the point at 4. So if you pick the point at noon and the point at 4, you find out that it is going up by 7 degrees over 4 hours, which is 1.75 degrees per hour. That doesn't necessarily mean that every hour is going to be perfectly 1.75 degrees, but when you average everything together, you will get 1.75 degrees per hour. Then we went between noon and midnight. Even though the temperature goes up and then it comes back down, and sometimes it might go up a little bit, and sometimes it is a zero slope. For example, between 2 and 3 hours, that is going to be a zero slope. The temperature does not change at all. When you look at this, you find it goes down by 11 degrees over 12 hours, which is going to be negative 0.92 degrees per hour. That would be the average, even though it's going up sometimes and down sometimes. If we look at the average, it's going down by a little less than a degree per hour. Now, part 2, we actually had already answered. We found out what the rate of change was between 4 and 6 and 6 and 10, and we found out that between 4 and 6 was actually faster. You're not looking at the overall change. You're looking at, they said, when is it going to be faster? Now what we had here was we had this graph that had both the population increases for California and for Texas. So what you were supposed to do is find out these different rates of change. I messed this up like 10 times. I kept not paying attention to what they were asking for. So on here, it's asking from 1970 to 2010. So you're going to want to find the change in dependent, which is population, over the change of independent, which is number of years. If you look for the California line and you are at 2010, that is at about 38. And then at, let's see, 1970, it's about 20. So you subtract those to get 18 meaning there's 18 million change over the 40 years. And that gives you a unit rate of 0.45 million per year. While 18 million over 40 years is a perfectly good rate of change, it's not the unit rate. It's hard to go over and compare two different things. For Texas, when we're looking at this, it's 25 million was the end. At the beginning, I thought that was about 11, so that's 14 million change, and that is over 40 years. And when you check that out, you find out that it is 0.35 million per year. In this situation, what does the rate of change mean? It's talking about the population change per year. Now, this does not necessarily mean that there's going to be exactly that amount per year, but we're looking at the average over 40 years. The next one says, which state's population grew more quickly between 1900 and 2000? So not only are we going to want to find a rate of change, but you're going to want to find out the unit rate of change. And me, silly me, I accidentally went from 1900 all the way to 2010. I don't know if maybe you did that as well, but then finally I realized that we're supposed to go to 2000. So I thought that was about 34 million at the end when 2000 happened, and about 1 million at 1900. That's 33 million change over 100 years. So that gets you 0.33 million per year. And Texas, when you look at Texas, it looks like at 2000 it's about 21. It's about 3 at the beginning. So it's 21 million minus 3 is 18 million change. And that was over 100 years. That's 0.18 million per year. So you can see that California was growing faster. The next thing that we did was we looked over this graph right here. I snatched this off of Google. It basically was showing the cost of Apple stock over a period of time. So they had the price October 18th in 2021, and then we had the price in October 18th, 2024. And when we were looking at that, we had to do change of dependent over change of independent. And I knew that it was change of cost over years. It's not like Father Time is waiting to go to the next year, but it can't because Apple stock hasn't gotten there to a certain place yet. Apple's important, but not that important. So when we look at this, I'm going to find out the change of cost or value of the stock. And I found out that was $90.16 over a period of 3 years. So that comes out to be $30.05 per year. Now, that doesn't necessarily mean that it is guaranteed to be $30.05 per year. Maybe 1 year it actually went down. It looks like between 2022 and 2023, the beginning of both, it went down in its price. But over time, the average was going to be $30.05 per year. So hopefully this is making sense. You want to do the change of dependent over change of independent. You can either do that as rise over run, looking at a graph. You can do it using y2 minus y1 over x2 minus x1. But just make sure you're doing change of dependent over change of independent. And it's good to get down to the unit rate so that you don't have to see what's happening in 3 years or 5 years or 10 minutes. You want to see what it is per unit. So it's unit rate. Now on this one right here, they weren't necessarily asking you to calculate what the rate of change was. It just wanted to know if it was positive, negative, or 0. And if you look between n equals 1 and n equals 5, it's going down. So it's negative. When between 5 and 7, it's going up, so that's positive. Between 10 and 20, it's going up, so that's going to be positive. It's kind of hard to see here, but between 20 and or 15 and 18, it looks like it is not going up and it is not going down, so that would be 0. And then between 20 and 24, it is going down, so that's negative. This next one is asking, was the person walking faster between 20 seconds and 40 or 80 and 100? Now, faster means that more distance or the same amount of distance is covered in less time. So more distance, less time. That is looked at by looking at how steep something is. So when we look at this and we're looking at the steepness, it looks like between 80 and 100, it's steeper. The next one is between 0 and 40 and between 40 and 100. And when I calculated the slopes between those, I found out that it was actually going to be steeper between 0 and 40 seconds. The next one was just asking if you understood the concept of positive and negative rates of change and what it would look like in a real world situation. So go ahead and check these. When the squirrel is running up the tree very fast, the average rate of change is large and positive. When the squirrel starts and ends at the same height, then that is going to be a rate of change that is 0. Things may have happened between that, but when we're looking at the average rate, it's going to be 0. When the squirrel runs down the tree, the average rate of change is negative. And when the squirrel runs up the tree, that is going to be number 3, which is the rate of change is small and positive. Okay. So, oh, sorry, it says the squirrel runs up the tree slowly. That's why it was small and positive. Now in these ones right here, you can check your answer on the first one. I found out that the change in percentage was 8.2% down over 8 years, and I was able to find that unit rate. This is talking about the percentage of voters that are between 18 and 29 over time. So there's that. Number 2 and 3 are going to be a little bit trickier because you were supposed to pick your own values and calculate. Just make sure that in the first one, it says that you want a negative rate of change. And the number 3, you want a positive rate of change. So make sure you pick things and your work is showing a rate of change. And it's either negative or positive, depending on what they want. Next one is just some review. It says Jada walks to school. The function d gives her distance from school in meters as a function of time in minutes. What does it mean if it is d of 10 equals 0? 10 is the input, which is the number of minutes, and 0 is the output, 0 distance from school. So at 10 minutes, she is at school. And the next one says, Jada walks to school. The function d represents a distance from school in t minutes, which equation tells us Jada is 600 meters from school at 5 minutes. 5 is the input, so it needs to go in the parentheses, and 600 is the output. So that would be A. Hopefully that made sense. Thanks for watching.